Hello, everyone. Happy Thursday to all of you. So in this video, I just wanted to give a video solution to a problem shown to me by one of my students who needed help with this problem. So this is an integral calculus problem. We're being asked to find the area between two curves. So this should be y squared is equal to x plus 1. And then we also have y squared is equal to 3 minus x. So those are the two curves that we are being asked to find the area bounded by. So up until now, we've been doing everything in terms of x. We've been solving integrals involving functions that are in terms of x only. So for example, we know how to find the area of something like this. So if we're starting at A, ending at B, and we're expected to find this area, we want to start by drawing a representative rectangle, because we know that a definite integral gives us the area under the curve by approximating this as an infinite sum, by approximating it as the sum of an infinite number of really skinny rectangles, where the base of the rectangle is given by dx, the height of the rectangle is given by f of x. So the area, as we know, is given by the definite integral from a to b of our integrand, the function to be integrated, times dx. But then we are going to be looking at things a little bit differently in this case. We're no longer going to be looking at things in terms of x. We're going to be looking at things in terms of y, because that's what the problem asks us to do. They specifically ask us to find the area of the function given by an integral with respect to y instead of with respect to x. So that is what we will do. Sorry, Zoom does not want to be my friend today. Having to move some stuff around in order to erase what I want to erase. There we go. Okay. So this is a completely separate example. We do not need this at all. So whenever I'm faced with a problem like this, I want to look at my variable of integration, and I want to make sure we are strictly in terms of that variable. So in other words, instead of having a function y in terms of x, we want to have a function x in terms of y. So we want to make sure we solve for x completely before we're ready to set up the integral. So for this first one, I'm going to start by subtracting 1 on both sides to solve for x. So we're given the following. We're given x is equal to y squared minus 1. And then for the second one, same thing. We're going to solve for x. And when we do that, we end up with x is equal to 3 minus y squared. Perfect. So now we're ready to integrate, but before I even want to integrate, I want to take a look at the graphs of these functions to understand what we're dealing with, and gives us some sense about where the points of intersection should be, because they will tell us the best possible choices for our limits of integration. So I'm going to go to Desmos. Desmos is really handy for this kind of thing. They graph the functions really well, and they give us a wealth of information we need to help us through this kind of a problem. So let me share my screen on Google Chrome. There we go. This is Desmos. So we have x is equal to y squared minus 1. Ordinarily, we would be dealing with the top versus bottom situation. So we know if we're dealing with the area between two curves and we're integrating with respect to x, it would be the top function, the area of the top function minus the area of the bottom function. But in this case, it's going to be a little bit different. When we're dealing with things in terms of y, we're actually going to be integrating the right function minus the left function. So we're going to be doing the integral of 3 minus y squared minus the integral of y squared minus 1. And by this point, we're really used to looking at the intercepts to tell us the limits of integration. So if we're dealing with things in terms of x, this would be our a, and this would be our b. We would have our integral from a to b just like that. But the problem is we're not doing things in terms of x right now. We are dealing with things in terms of y. So it's going to affect the way we solve this problem. So instead of picking limits of integration on the x-axis, on the x scale, we're going to be picking limits of integration that are on the y scale. So we're going to be starting with this value. This is going to be our a, and this is going to be our b. So we're going to be integrating from negative 1.414 to positive 1.414. And this is what our representative rectangle is going to look like. So if we're dealing with things in terms of x, it'll be a vertical rectangle. But because we're dealing with things in terms of y, it's going to be a horizontal rectangle, but the theory is exactly the same. dy is going to be the width of the rectangle, And then this value right here is going to be the length of the rectangle. So now that we have this information, let's go back to the whiteboard and solve this integral. Give me a quick second. All right, so back we go. So we know from looking at the graph that the rightmost function is 3 minus y squared. So we're going to set up the integral to be this. A for area is equal to the definite integral going from a to b. So it's going to be going from negative 1.414 up until positive 1.414. Those are the limits of integration on the y side of things. So like I said before, whenever we're dealing with things in terms of y, we do the integral of the rightmost function minus the integral of the leftmost function. So the rightmost function is given by 3 minus y squared. And then the leftmost function is given by y squared minus 1 dy. So that's the hard part, believe it or not. We already did more than half of our share of heavy lifting. Setting up the integral is by far the hardest part. And after we do that, all the integral rules that we knew up to this point still apply. We still integrate the same way we normally would if it were dx instead of a dy. So we did the hard part already. Now let's integrate. So we're going to find the antiderivative, and then we're going to do f of b, which is our high endpoint, minus f of a, which is our low endpoint, to give us the area bounded between the graphs of these two curves. So let's go ahead and do that. So the integral of 3 is 3y. The antiderivative of 3 is 3y, and then the antiderivative of y squared is y cubed over 3. And then the antiderivative of y squared once again is y cubed over 3. And the integral of 1 is just y, so that's going to turn into a minus y. And then we have our endpoints. We have negative 1.414 and then positive 1.414. So now we just plug things in and we do the nitty-gritty, tedious arithmetic calculation part of things. So this is going to be going to give myself a little bit more room. So we have 3 times 1.414 minus 1.414 raised to the third power divided by 3. Minus the same thing, 1.414 raised to the third power also over 3. Minus 1.414. Making sure I close all my parentheses and brackets. When you study computer science, you're just in the habit of making sure all your brackets and braces and parentheses are closed to make sure your compiler doesn't yell at you when you're ready to compile your code. So I've just been really good about being in the habit of that kind of thing due to studying computer science for so long. I am a certified geek. I'm as geeky as they come. Well aware of that fact. So now we're going to do the exact same thing, but we're going to plug in our low endpoint, the negative 1.414. So we have 3 times negative 1.414 minus negative 1.414 raised to the third power over 3. And then minus negative 1.414 to the third power over 3. That looks like a 7. That's not supposed to be a 7. There we go. And then we're going to subtract y. So in this case, we're going to subtract negative 1.414. And because this is meant to be a calculus video, not an arithmetic video, not an algebra video, I'm going to skip over the tedious part where I punch all of this into a calculator, and I'm just going to jump right to the final answer. So after we compute all of this, we end up with an answer of 7.542. And that is the answer. That's the area bounded between two graphs. Hope you found this useful, guys, and I'll see you in the next video.